Hello, somebody there? Hello?
Hello, this is Lacrosse.
Hi, Lacrosse.
This is Scott?
Yes.
Hi, Scott. This is Joyce.
How you doing today?
I'm doing fine.
You guys getting a little snow over there?
It's a little snowy out. Yeah, not too bad.
Ah.
Okay, I have to go get my password and all that. No.
Hello?
Hello, this is Pat Miller.
Hi, Pat.
I'm working on getting everything hooked up. I think I'm about in.
Okay. Good morning.
Good morning.
This is Scott Sanford.
This is Mark Pomerlow.
How you doing, Mark?
I'm doing good.
This is Pat Miller, and I'm having trouble. I've got the PowerPoint pulled up, and I've got the audio. I've got the WIS line web, and it's asking me about Java, and it said I had that. And somewhere I was supposed to click join the meeting, but I don't see that anywhere.
When you log on, it actually should kind of go right into the bring it up, I think. I haven't used this a lot before, so
Okay.
I'm learning as we go too. Because I know in some cases when you first signed on, there was an update you might have to do. Let me pull my...
So there's something besides the PowerPoint looking thing, or is that it?
No, what you should see is a PowerPoint.
Okay, it says energy conservation for greenhouses.
Yep.
Oh, okay, I'm there, so.
Yeah, and then you got the voice on this end.
Right. Okay, I should be fine then. Thank you.
Okay.
Did you get the floor for it?
Let's see, is Holly on the line?
I can get one without that for right now.
Is Steve on the line from Spartan High School?
He'll be out there. Do we have to do dancing?
It's right where they...
You go out there.
This is Scott Sanford. How many we have on the line here?
Well, Lacrosse is here.
Lacrosse is here. Okay.
We've got, I think, 6 people.
Wow. A crowd.
Well, it's going to be a great presentation.
Jake County is here with 3 people.
Which county?
Jackson?
Jackson, okay. We're expecting about 20 people. I don't see that many people. I got 12 logged on at the moment, so we'll give them a couple more minutes.
Taping for Clark County, just the audio. He had another commitment today.
Okay. Well, I'm going to record the thing, so you can go back and pull the recording up. Email me.
Oh, okay. I don't need to tape it then. He can get that from you.
Yep, he can get the video and audio.
Oh, okay. I'll let him know that. Who should he contact?
You can send me an email.
Okay, sounds good. Thank you.
You're welcome. Kevin, you on?
Yes, I am.
Okay.
I got the video up, but there's nothing happening yet, so I'm assuming you're waiting to start.
Yep, I'm kind of waiting. There's supposed to be about 20 people, but looks like I have about 9 or so right now.
Okay.
So I was going to wait a few minutes.
Okay, so do you have me, show me as being logged in on your computer?
Yep.
Okay.
So you should have the PowerPoint.
Yeah, it's shown on screen, so if we want to ask questions, we can do it on the computer or over the phone.
Yep.
Okay.
Well, give people about 3 more minutes, and then we'll get going here. Hello, somebody just joined us?
Yeah, this is Kate Field.
Hi, Kate.
Hi.
We're just waiting a couple minutes for a few more people to join us, and then we'll get going.
Do I need to do this phone and a headset, or did I need to call it?
No, basically the audio is through the phone.
Oh, okay.
The video is through the computer. They don't have it tied in with voiceover.
Oh, okay. So it has to be on the phone.
Yeah.
Okay. I'll take this headset off.
Yeah, I'm not sure why our system does it that way, but that's what they do.
Yeah, well, that's what a lot of them do.
I think it's better voice quality because I think sometimes people have had problems losing the audio.
Yeah, and is this a long-distance call?
I don't know if they gave you an 800 number to call.
No, it's 608, so...
That's going to be a long distance then.
Yeah, for an hour.
I was surprised about that. Okay.
Yeah.
Let's see what I can...
it says a helpline. It's an 800 number. But the audio information number is 608. So I'm at home too, so it's not like, you know, work is paying for it. So.
Yeah, I'll have to find out about that for our next call.
Yeah.
Anyway, it's 5 after. Why don't I get going here?
Sure.
This is the longest segment of the 4 sessions. Well, actually, the last section will be a fairly long one too. We've got 3 sections that I'm going to do. The first one we're going to do today is just general energy conservation for greenhouses.
Great.
The next one is going to be on thermal curtains or energy curtains. And then the third one will be on biomass for greenhouses.
Right. I think I signed up for all of them. I'm a horticulture instructor at Gateway Technical College.
Okay.
And we have a pretty large greenhouse system, and we just had it reglazed about 2 years ago, and we're supposed to be getting a thermal curtain. I think we have it ordered in the works, and we're supposed to be getting, at some point, geothermal heat system.
Okay.
So there's a lot of things happening, and
all right.
I teach greenhouse classes, so I'll be able to use this in my classes.
Great. And then the last section we're going to be doing is on Eric Runkle from Michigan State University is going to talk about production methods.
Great.
To reduce energy usage.
Yeah, we're all looking at that.
Okay. So if everybody could, let's see, Jim's gotten a problem. Hang on a minute here. Jim can't hear. Jim, are you on the, well, if you can't hear, you can't. Hang on a second here. Take care of something. I'm not sure how to help Jim, but he needs to be on the phone.
Did he turn up his speaker?
I don't know. Well, let me I can find Jim's email, and then we'll. Okay, 2 seconds here.
Mm-hmm. All right. Well, we'll get going here. I emailed Jim, and we'll see what goes on. Okay.
If everybody could, if you can put your phone on mute, then it eliminates background noise. But if you do have a question, go ahead and come on the line. Or you can...
This is Jim.
Oh, hi, Jim. Okay. Well, basically, if you can... everybody can mute their lines while we're doing this, and then if you have a question, you can come on, or you can type a question. If you go up in the box that says Q&A on your header, you can get in there and type me a question if you've got a question in the middle.
How do we mute the phone?
If you got a mute button on your phone. If not, just we'll just go from there. So my name is Scott Sanford. I'm an outreach specialist here at the University of Wisconsin. I do energy and agriculture as my main job here. Greenhouses are just one area that I cover. So let's get going. This presentation is going to be on just general energy conservation. When we look at greenhouses, energy use is usually the second or third highest cost. About 15% of total costs for production. Can be, in Wisconsin here, it's probably in the neighborhood of $1 a foot for a spring growing season. But that all depends on the type of greenhouse you have. Space heating is going to be 70 to 80% of the heating needs of a greenhouse, and about 10 to 15% will be electricity. When we look at energy conservation in a greenhouse, we're always balancing horticultural needs with economics, because we can do a very well-insulated building to keep the heat in, but without light, we don't have growth. So we're always having a balancing of the environmental factors for growth versus operating costs and sometimes structural costs. The principles of, just a quick review of principles of heat loss. We have 4 main ways we lose heat out of a greenhouse. We have conduction loss, which is a heat transfer through materials, which is there's a value. Each material it can be assigned or is tested for a value, and it's listed as BTUs per hour per degree Fahrenheit per square foot. What you may be more common or familiar with is R value, which is the inverse of that. When you look at when I show you the U values, you're going to find they're around 1 or just a little less than 1. When we look at like a house construction, it would be a decimal point. So they invert it, so it's a bigger number. But either will work. If you remember, one's the inverse of the other. We also have convection heat exchange within the greenhouse, which is the exchange of air from air moving in the greenhouse from a solid surface into the air, which is a fluid, and then back to another body inside the greenhouse. The other is radiation heat loss, which is a transfer of heat between two bodies without direct contact. So sunlight's an example of that. And the other we're going to talk about is long wave or infrared radiation. The other place we lose heat in a greenhouse is infiltration losses. And this is exchange of air from the inside to the outside or vice versa. So we have leaks in the shell. We have cold air coming in. We have to warm it up to maintain the temperature inside the greenhouse. So those are the main principles. It doesn't matter what type of greenhouse, whether you have a hobby greenhouse, a standalone, or a large span. All these greenhouses are going to, those principles work on each one. Now, the first thing I want to talk about is structural efficiency. And basically this has to do with the amount of heat loss per surface area. When we look at a gutter-connected greenhouse, we have a lower ratio of floor area to heat loss area than we would with a standalone greenhouse. We basically have more surface area on a standalone greenhouse for the area covered, so we end up having more heat loss. And the question here is, what shape would have the lowest heat loss per floor area? And basically it turns out to be a sphere. However, making a greenhouse in a sphere shape doesn't work very well. So we tend to use a square or rectangle. Square is going to be the most, have the least amount of surface area per floor area covered. So let's put some numbers on this. I chose basically a gutter-connected greenhouse with double IR poly, which is the best you can do in a poly. About a half acre of greenhouse with a standard power vent heater, just to give you an idea. So I've got 8 standalone greenhouses versus a gutter-connected greenhouse. And I get, you can see from the energy saving on the slide, I get about an 18% energy saving. Then, depending on what you're paying for LP gas, that could be, you know, $3,000 or $4,000 for energy. You notice in here, my gutter connected, I made it almost square. So I try to optimize this to show you what that effect would be. The other thing when we're putting up greenhouses is orientation. General recommendation is a single span should be east-west, and that's basically to maximize sunlight. When we have the wintertime sun, we're trying to maximize. If we have it the long way, we're going to get the most amount of sun exposure into that greenhouse, and basically so we pick up light for the plant growth and heat. If we gutter-connected greenhouses or multiple bay greenhouses, the general recommendation is north-south. And this is because the gutter, which they're about 12 inches wide or so, are going to have a shadow in the greenhouse. And if we have them east-west, that shadow, because the sun kind of stays in about the same level in the sky during a winter day, it's going to cast a shadow that basically won't move. But if we put that greenhouse north-south, then that shadow moves throughout the day, so we don't have a spot where we have less growth. Glazing materials. We've got to cover our greenhouse with something to provide sunlight to come in, but yet maintain heat. And they're basically broken down into two classes. One would be a single pane, and the other would be a double type material. So I picked the two extremes here for my example. One is a glass, and the other is a polyethylene, double polyethylene film. So anything with single pane is going to have a heat loss of about 1.1 to 1.2 BTUs per square foot per hour per degree Fahrenheit. Glass is basically the gold standard for greenhouses, mainly because it has high light transmittance. And percent of light is percent of growth. The disadvantage of glass is the weight of it and the cost for holding it up. It does have very long life, which is an advantage unless you get a hailstorm. If you got large hail, that could cause a problem. But it is basically the gold standard. When we look at polyethylene film, it's going to have the shortest life, although it's going to have a reasonable heat loss. Standard film is going to be about 0.7. If we have the IR rated, it's going to be down around 0.5. It's low cost, but it has lower light transmittance. And I think my next slide will show you that as a table that has the different types of materials used on greenhouses. We've got glass.
We're missing, we don't show slide 3 page 3 doesn't show.
Page 3 doesn't show. You're
so
not.
Our last slide is structural efficiency. I don't know about anybody else, but when you go to 3, there's nothing, it says an error.
I see it fine. No.
I see it.
Huh.
Glazing material comparison.
Right.
Yeah.
Yeah.
You might you might go out and come back in then to see if it reloads all right. I apologize for that. Oh, you know what I didn't do? I didn't start a recording here. Oh no, somebody did. Okay. Okay. So one of the things with we've got glass, acrylic, polycarbonate, fiberglass, and polyethylene. One of the things you'll see is that all these have about the same. Doesn't matter what material. All the single panes are about the same same heat loss. Hang on a minute. Okay. And when we look at the light transmittance, a single pane is going to be about 90%, almost clear across the board. A double pane, the light transmission is going to be about 78 or 80%, with a few exceptions. Acrylic is very good in that regard, although it's not as well used. You're going to see on life of the lifespan, they vary depending on the material. Polycarbonate is one of the ones that is used extensively in the industry and has a life of about 10 to 20 years. And usually it fails by yellowing as much as anything. The other column I want to point out is this thermal transmittance. That's basically long-wave radiation that after the sun heat warms an object into the greenhouse, it's re-radiating the long-wave radiation from the heated objects out into the greenhouse. Everything except polyethylene is really good at reflecting that back in, but a polyethylene film is not as good at reflecting that in. But the industry has come up with they put some additives in to reduce that, and we're going to talk about that here in a minute. So, main infrared pathways. We've got the sun on the outside. It's going to come through the glazing. It's going to warm the objects, and then the long dashed lines are basically my long wave radiation radiating back into the greenhouse. So glass or polycarbonate is going to reflect that. We get to the polyethylene films. A lot of that long wave radiation will go right through the greenhouse, with the exception over here if I've got condensation. Condensation will block long wave radiation, but it also blocks light coming in. It can reduce the light level coming in by 20-25%. So condensation at night's not a problem, but condensation during the day is. So that we'll talk about that more in a little bit. So I think I covered most of this. Polyethylene films are the worst. If we go on to, most companies make one or two products that have an additive to block the long wave radiation coming into the greenhouse, and they call it a thermal or an IR type film. This can reduce heat loss, long wave radiation heat loss, by about 15 to 20%. They cost about $1.50 to 2 pennies a square foot. They'll pay back in about 3 months or one season. It basically works out to about, to cover a 30 by 96 greenhouse, works out to about $40 more for the one layer of poly or IR rated materials, and works out to about $10 a year. So it's well worth the investment. And these are often combined with a anti-condensate coating or something that reduces the surface tension so that condensate will run off the greenhouse glazing. One of the things to point out is the IR film should be on the inside. It should be the inside film, mainly because it has the anti-condensate additive on it. So it has a up and a down side. So that's important. Because I had a grower that had a company come in and put it on. They put it on the outside, so it didn't help them. Solar gain, I've already mentioned this. Basically, percent light is percent growth. So when we look at different materials, as we go to a double wall material, we're going to gain in energy conservation, but we're going to lose in the fact that we have less light coming into the greenhouse. Now, we have auditors here in Wisconsin that are in the field, and they've realized that there's a triple-paned polycarbonate, and they were starting to recommend it. Well, one of the issues with that is you're going to lose another 5% in light level. And during February and early March, we probably can't afford to lose that because we're going to actually extend the growing season if we lose that light level. So this is that horticultural economic balance that we talk about. And one of the objects there is there's a better option, and that would be thermal cartons, which we'll talk about later. Condensate, if you don't have anti-condensate films, you can buy, there's a material you can buy and spray onto the film to reduce, or the polycarbonate to reduce the condensate buildup. We don't necessarily have a problem with dust here, but in some parts of the country they do, and there are anti-dust additives, basically to keep it off the outside of the greenhouse. One of the things I'll point out on a double poly greenhouse is we inflate these with a little blower. And the typical thing is they are put on the inside of the greenhouse, pulling in inside air to expand those poly films. One of the problems with that is that's the highest humidity air, and when it comes in contact with a cold air next to the outside film, it condenses and restricts our light level. So a better way to do it is what's pictured in this first picture, is to have that, so the inlet, you can see here's the inlet, here's the blower here, so that we're pulling outside air in to inflate this. That's going to be lower humidity air, so you have less condensation problems. The other thing is to make sure our panels are inflated properly. And sometimes when they come across a corner or something, that acts as a restriction. So putting a jumper in, like we have pictured here on the right, will ensure that you have adequate pressure to inflate that area fully. So that can be an issue. Glazing materials versus infiltration loss. Infiltration loss can vary widely on greenhouses, and a lot of this has to do with maintenance. We get leaks, infiltration rate, we get leaks through louvers and doors and holes and gaps, and actually underneath sill boards is a big one as well. But it also is affected by the type of glazing material and the number of joints we have, essentially. So you're going to find something like a polyethylene film, there's very few joints. So it actually has the lowest air exchanges per hour, versus glass is going to be much higher. Now, new glass, you've got brand new joints, it's going to be good, but when we get aged, we can get higher infiltration losses. One thing that can help us reduce infiltration rate is windbreaks, and this is a long-term thing, and it depends on how much area you have. But if we can put a row of trees upwind of our greenhouse, we can reduce the pressure on the greenhouse somewhere between 5 and 10% during windy periods. So infiltration rates, it's kind of a maintenance thing as much as anything. Roof vents, these roll-up doors that's pictured on the top are terrible because they leak along the edges of the door and across the top. So they're nice because they're easily put in and they don't have the door swinging overhead, but they are terrible as far as air leaks. The other is in the lower picture. It's maybe hard to see, but there's a gap here between the sill board and the ground. So there's air coming through there. So getting the dirt up on that sill board and possibly have, if you're using polyethylene, you can bring it down onto the ground and then throw some dirt on top of it to hold it there. But a lot of this is basically a maintenance issue. Doors, if you have a door coming into a greenhouse and you just have dirt on it, putting a wooden sill there to maintain gap. Now we do need some air in a greenhouse for heaters, depending on the type of heater, but we'd rather have those as planned inlets versus unplanned. So the other thing is, if we have a glass greenhouse, one of the things we can do is put a piece of polyethylene over top of the glass for the winter. Now, we have a big savings here. If we reduce our infiltration rates, we will reduce the light transmission through there. So it's going to go from about 90 to about 78 or 80 by putting a piece of poly over it. But here's a case where the energy savings is probably worth it to do that. Conduction heat loss, basically we have it through the glazing materials, but we also can have it through the walls. And one of the things is, if we're growing plants on benches, we really don't need to have glazing from the bench down, because under the bench we don't need light. So one of the things is to insulate the walls up to the height of the plant. So this can be a simple 2x4 stud wall with some preferably foam, because foam won't absorb moisture as well. If you already have a greenhouse, you can take a foam board and lay it up against the wall, but it has to be sealed tight to the wall so air can get behind it. On new greenhouses, putting a piece of foam board along the foundation will reduce heat loss, especially if we're growing in the ground. And I say here for new construction, when we do the math on the heat loss, it doesn't pan out for existing construction because of the cost of installation. If you're doing new construction, before you start, you run down with a trencher and you make your trench and drop your foam board in it and you're ready to go. It's quick and fast. If you've got an existing greenhouse, most of it's probably going to end up being by hand, so it's expensive. The warning here is that foam board is flammable, so we need to cover it. You can buy some that has a foam or a aluminum sheet over the top of it that's secured to it, or sometimes they come with like a fiberglass layer on top. It's something to help protect that. Thermal curtains, I'm not going to spend any time on today because we're going to cover it next Tuesday. But this shows you one of the things is thermal curtains can reduce, it's the single biggest change you can make in heat loss in a greenhouse. They can save somewhere between 30 and 50% in heat loss during the winter, and then you also have the advantage of possibly less ventilation and light control during the summer. So they're good because you can use them in two places, depending on the length of your growing season. Next we're going to talk about heaters. There's quite a bit we can do with heaters as far as saving energy and reducing our costs. Unit heaters are one of the most popular because they're low cost, they're easy to install, they can be easily staged, and they're very reliable. So there's almost every greenhouse you'll see some type of unit heater someplace. So when I first started looking at this, there's a number of different types of unit heaters, and there's very little dollar difference between some of these. So up in the upper right-hand corner, we have a gravity vent, which the one thing you'll see about these is they have a big pipe coming out of the back of the heater, and it basically comes out and goes out of the building. That's a gravity vent. The next step up from that is a power vent, which is down here in the bottom, and it's got a little blower on the exhaust that meters the air out of or through the combustion. And one of the things with those is when the burner isn't firing, that fan blocks atmospheric air from just freely going out of that through the heater. The next one is a separated combustion. It's a power vent heater. Up on the top here, so you can see the fan, but it also has a line coming in that brings fresh air in. And for many greenhouses, if you're doing a lot of fogging, this is highly recommended because of the corrosive nature of some of the sprays we use in greenhouse. So one advantage of this is if you've got, especially if you're in a windy spot, this will affect the burner a lot less, but also brings in outside air. These first two, we're using inside air to combust it. So we're heating the air and then we're using it to combust our gas. So we're losing a slight bit of efficiency because of that. One of the new things in the market is a high-efficiency condensing type unit heater. Condensing type heaters have been in residential heating systems for a number of years now. but the greenhouse industry has only had a few manufacturers making them. So one thing with these, you can see we've got a fresh air and an exhaust, and they are often PVC tube, and it will have a drain on the bottom. And essentially this is a separated combustion heater with an extra heat exchanger that condenses some of the moisture out of the flue gas to basically get more heat out of it. When we evaporate water, it takes 970 BTUs per pound of water to evaporate it. If we can pull some of that back out, that's heat into the greenhouse. So that's how this works. Well, when you look at the literature on some of these, what struck me when I was looking at it is that this gravity vent and this power vent have the same efficiency, and there's $100 difference between them, roughly. Now, the gravity vent's no longer sold because of the new energy standard that was passed in Congress. These gravity vents couldn't meet it, but there's a large installed base. But when I started looking at these, there's $100 difference, so I was trying to figure out what the difference is. Why would you spend an extra $100 to get the same efficiency? Except that, if you got a power vent, you have more leeway as to where you put it. So my next slide's going to show that a little bit. Separated combustion, about 82%. Actually, the new ones are 80% now. And then we've got the high efficiency one, which is definitely another 13% higher. And then we've got associated costs with them. So I was trying to figure out why you'd want to spend more money or what the advantage is. Well, one of the things the manufacturers I don't think do a very good job of is talking about seasonal efficiency. If I've got that gravity vent heater in, I've got air running through that heater whether it's firing or not. And you lose a lot through that just because it's running air through it all the time. So that's the difference between the power vent and the gravity vent, is that little fan blocks the natural buoyancy of air going out of the greenhouse. So for $100, that's well worth the investment. And then the separated combustion is 80%. We're not using outside air, so we gain the 2% from over the power vent by bringing air in from the outside. And then we have the high efficiency unit. So question is, let's do a little case study here to show you what the differences is, because I've been in this business long enough that basically nothing happens. People won't invest in this unless it's economical. So I got a 30 by 96 greenhouse here in Madison. One heater can supply the heat 90% of the time. Got a daytime of 68 versus 60 at night. I'm assuming $1.50 for propane, and a growing season of February to June. So when I look at that with my incremental costs, I've got two heaters. So I'm going to compare gravity vent's going to be my base. I've got a power vent, separated combustion. I've got a high efficiency unit. And then I paired up a high efficiency unit with a power vent. And I'll explain that in a minute. So you can see in my energy savings, or my fuel savings, there's quite a savings here. So over the power vent, there's a 16% savings. Separated combustion is 19%. High efficiency jumps up another 11%. And then, one thing is that if I use a condensing unit with a power vent as my backup, or my second heater, so I run my high efficiency condensing unit as a primary heater and my power vent as a backup heater, I can gain almost the same efficiency as using two high efficiency units. So when I look at the payback for these, and this is simple payback, nobody should ever have bought a gravity vent because it pays back in basically a month and a half. Separated combustion is the longest payback, even compared to the higher cost of a high efficiency condensing unit. But when I pair the two of those, I get a very nice payback because I'm taking advantage of the high efficiency unit for 80 to 90% of my heating needs, and then 10%, that last 10% I'm using on the power vent. And I also have a backup heater by having two of them. Now, all's not lost. If you have a gravity vent heater, there are companies that make upgrade kits. So Modine makes an upgrade kit, and you'd have to check on some of the other ones. They're a little more pricey than a $100 price difference, but they'll pay for themselves in a season or two. So, well worth the investment. And they just attach. So the basic heater, there's no difference in. It's just by adding that fan on it, helps meter the air and reduces the heat loss when the heater isn't running. Now there are non-vented heaters out there that claim to be 100% efficiency or 99% and 20% fuel savings over traditional heaters. They work, people use them. The biggest challenge with these is that they're putting moisture in the air, which can cause problems with diseases. Now they're also putting CO2 in the air, which tout as well, plants need CO2, but 80% of our heating is at night, and plants don't use CO2 at night. So yes, it can be used as a CO2 generator, but it's not generating most of the CO2 when the plants are using it. So one of the other issue here is it's putting the products of combustion into the greenhouse. Now these are very high efficiency and low combustion rates of carbon monoxide and all the other stuff. But they do have to have, if they're either going to have a separate inlet to pull outside air in, or they have to be interlocked with a vent so that the vent opens when the heater runs. Well, as soon as you do that, you lose some efficiency because now you're bringing cold air into the greenhouse that you have to reheat. And on the bottom here, it has suggested area for how big that vent should be. So one of the things we might want to look at is we have a high efficiency heater that runs at night, and we pair it with one of these non-vented heaters to run during the day. So we can switch which heater is the primary heater. And if we have a centralized control system, we can do that. Now I've occasionally had worked with Amish or people that have non-electric greenhouses, and there are small heaters that can be used for there, both vented and non-vented. If you have a non-vented, you still have to have an air intake, just like the non-vented one in the previous slide. And they do make heat exchange or thermostats. They're usually battery operated. So if you've got a little hobby greenhouse or you're working with Amish, these are a possibility. Now, they're relatively low BTU per hour capacity, so you're going to need a number of them. If you don't have electric to have fans in it and you have a large greenhouse, you're going to have problems with heat distribution. So you may need a number of these anyway in the greenhouse, so you're going to want to spread them through the greenhouse. But they're going to be about 80% efficiency, depending on how much air I bring in. Now, often I've seen where people in emergency cases or hobbyists try to use a portable type heater. Kerosene or oil are not recommended because the products of combustion of these contain ethylene, which will harm many plants, especially plants like tomatoes. They also have sulfur dioxide and nitric oxide. These are meant to be in an area that's well ventilated. If you need to use something, use a natural gas or an LP type heater or backup, because these heaters and all these heaters are going to require venting. If you starve a heater for oxygen, you'll get incomplete combustion, regardless of the type of heater. When we start to talk about heating in a greenhouse, often we've got a unit heater and it's kind of just blowing in the air. Sometimes they're kind of mounted up in the peak. Well, the plants aren't growing in the peak. They're growing down on the floor on a bench. So anytime we can lower the heat and get it below or at the level of the plant, we can save energy because we can lower the overall temperature in that greenhouse. We make this little micro environment. So what this picture shows is a mat on here. It's got little tubes and they've got supply lines along the side here that bring the hot water to. Now, a lot of people use these for propagation benches, but they could also be used for general heating of crops. Anytime, as I said, we make this little micro environment at the plant level. So it can be in floor. It doesn't have to be a concrete floor. You could bury the hydronic tubes in the floor and grow on the floor. You could do it under bench, either forced air or hydronic. Hydronic is hot water. And studies have shown, this was a study in Louisiana which doesn't have a lot of heating. They found 7% increase in the yields of tomatoes. But the same thing can occur in floral plants, that they grow faster. Now, when you do have bench heating, you tend to have more watering because it dries the pots out faster. Or you may have to have a media that holds the water a little better, holds a little more water, because it will dry out. With under bench, we can use polytubes under the bench. I'm going to show you a picture of that in a minute. But it's approximately equivalent to reducing the temperature of the greenhouse by about 5 degrees. So you can run the greenhouse cooler. Now, if you have in-floor heating, on a really cold night, it can't keep up. So you're still going to have a unit heater to heat the air. So a night like we're going to have in the next couple of nights, where it's down around 0 at night, in-floor heating, especially if it's in concrete, typically can't keep up. An under-bench heater system, you'll have a much better job of that, depending on the surface area you have available. So here's a picture of a unit heater set up to blow under the bench. So this comes down and into a polytube under the bench that runs the length of the bench. Now, one thing I'll point out is unit heaters can be propeller fans, or this one here. I should change colors here so it's more obvious. Has a blower. When you go into a polytube, it has a higher static pressure and will require a fan that can maintain higher static pressure in order to get that air down through the whole polytube and inflate it. So here's some examples of both homemade and commercial underbench heating. The one on the left is a commercial fin tube. So that's a fin tube right there. On the right here, this was an Amish or Mennonite. I think this was hooked up to a wood boiler. They just had some tubes in there. Here's somebody that got some old radiator fin tubes that they've just put on blocks under the bench. So it can be done in a number of different ways to get that underbench heating, besides the mat that I showed you earlier. And there's some commercial mats available that actually, there's one that'll actually do watering and provide heat. Here's an example of Amish are very inventive. I was amazed when I walked into this greenhouse. This whole system has no pumps. Over here, I'm going to kind of draw a box here on the side. That's about where the boiler was for this. He had a pipe coming out of the top of the boiler and into this pipe that runs along, and then down to a distributor on this end. And this was basically, once you got to here, is irrigation pipe. So he had pipes that run down underneath the bench to a header, and this header came back along and went back to the furnace. So the whole thing worked on natural thermal buoyancy. So it was very unique. So, you know, if you're inventive, you can come up with some of these things. Maintenance on systems. When we look at heater maintenance, we can, especially if we're using boilers, there's significant savings we can make just in maintenance costs. So one is to insulate pipes and ducts in head houses where we don't necessarily need the heat. Clean air heat exchangers. So even on the unit heater, the heat exchanger surface area, blow them off with compressed air. Some motors and fans may require some lubrication. And if we have a boiler, we typically need to open those up once a year and clean out the fire tubes. Basically to use a wire brush that you run down the tube to get rid of the soot out of there. And the soot acts as an insulator and reduces the heat transfer rate. If we have steam system, steam traps can leak and cause problems with or increase our heating demand, so maintaining those. And if we have any kind of heater, especially oil burners, checking the nozzle, the fuel filter, the pressure those we're operating at. Same thing with LP gas, make sure the pressure is correct so we're getting a good flame. Thermostats should be checked on an annual basis to make sure they're accurate. And, basically depending on how far out a repair a system is, there could be up to a 20% savings by just doing the maintenance. Now, one thing I'll point out here is I talked about air inlets before. If I walk into a greenhouse and I can smell the products of combustion, that means, and it's going to happen on a night like tonight or tomorrow night, where you're very cold up here. In Wisconsin, we're supposed to be down around 0 or a little below. All the heaters are going to be running almost maxed out. And if I walk into the greenhouse and I can smell the products of combustion, that means I don't have enough air inlets for that heater. So that's an indication that I need to provide more air inlets. Now, I can make those so that they don't open until the heater comes on, and I can actually duct them so they're right into where the heater is, but that's an indication. On a high-efficiency basis, there are high-efficiency boiler systems out there. This is pictured a couple of them. They're 90% plus efficient, and these can be tied in with if you're doing under-bench heating, this can provide your under-bench heating, but it also could be used with an air exchanger to provide your backup heat when the under-bench can't, or in-floor heating can't keep up. So they're condensing boilers. They're up to 98% efficient. And if you've got an old boiler, one of the things that we've done here in Wisconsin with our energy conservation program is we'll come in and do it an add-on to an old boiler. So we'll make this new high-efficiency heater, like these here. We'll set them up as a primary heater. So when the system first calls for heat, those will be the first boilers to come on. Now, if it can't keep up with the heat, so say my set point is 60 and it cools off to 55, then the old boiler will come in to make sure we maintain temperature. And with a good control system, you can be more accurate or less difference than 5 degrees. It could be 2 or 3 degrees. But the point here, and then these high efficiency boilers, you might size them for about 80% of your heating needs versus 100% of your heating needs, and that reduces your upfront costs, and you still gain considerable savings. So here's an example of an air-to-water heat exchanger that could be used with one of those high-efficiency systems to do. Now, the disadvantage, we've got to have some piping around the greenhouse to move water to and from the boilers. Infrared heating is also a possibility in greenhouses, although they can burn the leaves. Basically, infrared heating heats the objects, not the air. It works like the sun. And we have to be careful because if we can burn leaves. Now, there's issues with heat distribution along these systems. If you just buy any old one, they'll be hot near the flame end and cool as you get down the line, so they may not provide very uniform heating. The best places, I think, for these things are work areas, loading docks, work areas, warehouses. But there is a company out here that tries to promote bees in greenhouses, and they have a publication that might be a good resource. Let's go to the next one, environmental controls. One of the issues, we've got a lot of systems in our greenhouses. We've got heaters, fans, louvers, irrigation, CO2, lighting, etc. And we want to make sure that these systems aren't competing. So if we have individual thermostats, we could end up having the fans on when the louvers aren't open, or CO2 generator on when the fans are on, things like that. So we're not getting necessarily getting our full bang for the buck, because they all have different thermostats and they all might not be quite as accurate. One of the advantages of using a system like this GrowMaster or a central controller is they use one thermostat or one temperature sensor, and then they control everything from that temperature sensor. The other thing is they can be tied to a computer to anticipate wind or weather changes. So if the wind comes up, it might shut the vents. If you get shading, it might shut off the fans before it actually gets as cool as the fan setting is. But one of the things that Eric Runkle's going to talk about is diff, how we can use day-night temperature differential to save energy. Because we can reduce our temperature by 10 degrees, we can save 5% energy costs, and that's a production management issue. Basically, plants look at the average daily temperature, not the max and min within reason. So a 75 day and a 65 night is the same to a plant as 70 all the time. So that can be, we can use that to our advantage. Space efficiency, most growers actually do a great job of space efficiency, but if we look at the traditional long bench, we're going to have about 59% of that is growing area. Peninsular bench is 69% versus 81% for movable benches. Now, movable benches aren't going to be very good for retail space, but one of the things we could do is have these on rolling carts, and use these as rolling carts, and when it comes to growing after our production season, we roll some of these carts out and maybe rearrange them in a peninsular type arrangement to work during the retail season to get more into that greenhouse, so we don't have to, we get more out of the heat we put into it. So here's an example of a rolling bench or movable bench. It's got a pipe here that it rolls on, and then this is a cross beam underneath here. This is actually set up with that irrigation pipe here on the side, and this is the underbench heating here. So we've got everything in one type of bench. The other is racking systems we can use, or the other is overhead pots. That's another example of trying to get more things into a greenhouse. And some of these cable type systems actually have automatic waters. There's a water right under that red arrow in there. So it automatically waters the plants as well, which is a fairly labor-intensive chore. This system here has actually a pipe that runs along and runs back and forth in the greenhouse. So this one can only cover half the greenhouse, this pipe system over here, versus the cable system. You've got plants running the whole greenhouse. Circulation fans can be important. One is it's mixing air to keep from stratifying. If we don't have some air mixing, we got the heat rises, so we're going to have the warm air that we'd like to have down around the plants up in the peak of the greenhouse. So we can reduce our heating costs by getting that air back down to where the plants. And also by having some fan or air circulation, we can get leaves dry out faster after watering to prevent disease. So fans can be fairly useful in that regard, and you can use a paddle fan, a basket fan like we have over on the right, or a new entry into the market is a jet type fan, which basically puts a column of air down, and then it's supposed to hit the floor and kind of go sideways and horizontally. For ventilation fans, exhaust fans on a greenhouse, they're going to be required in many cases, but there's a large difference in the efficiency of fans. And the take-home message from this is that you can't look at a fan and tell what the efficiency of. There's actually Best Lab, which is part of the University of Illinois, has a lab that tests fans and publishes them. So you can go on their website and look up a fan and get the test results. The fans that they have tested, there's a huge difference for the same size fan in the efficiency of those. It's well worth going to the data to look before we buy a fan. Ideally, we'd like the larger the fan, the more efficient. And here in Wisconsin, we use a number of 20 or 21 CFMs per watt at a 0.05 inches of water pressure for our fans to consider them high efficiency. Motor efficiency is another one. If we have things that run long hours, standard motors are not very efficient. You can see here's a standard motor, 1/4 horsepower, which might be on a small fan. There's two companies out there that make high efficiency motors in single phase that are substantially more efficient. So one of the things, if we look at a fan, oftentimes a lot of the efficiency of a fan comes from being a higher efficiency motor. So if we have to replace a motor on a fan, we might want to go back to the original manufacturer rather than going to a third party to just buy any old fan or motor to fit in there, because it may not have the same efficiency. With greenhouses, with the ventilation maintenance, we've got fan maintenance, shutters. The shutter won't open and close properly, especially if it's a gravity one. Can reduce airflow by 40%. Belt tension can, if we get loose belts, reduce the air by 30% before they start slipping and won't provide any air. One of the things I recommend is to buy fans with automatic tensioner or retrofit fans with automatic tensioners so that it gets rid of that chore. Because a lot of those maintenance things, we get busy and we don't get them done. The other thing is, we got fans on a wall. We need to make sure that the weeds and shrubs and stuff are trimmed away so there's free access to the air to leave the building. And occasionally we'll have some of the older motors required some lubrication. Any fan or any motors inside of a greenhouses are considered a moist environment, and by electric code they should be totally enclosed motors. So that's an important thing from a safety standpoint. From the ventilation side of greenhouses, we can use shade curtains, which can also double as thermal curtains if they're on the inside. So this can be something you pull over the outside or the inside. We can use evaporative cooling pads, we can use misting, roll-up curtains, and open roof designs. Here's a picture of an open roof design here. This is about a half-acre greenhouse. Doesn't have any fans in it at all. There's enough thermal buoyancy to move that air out. The other thing we can do is use variable speed fans so that wintertime ventilation, we can reduce that so we're not over-ventilating the greenhouse on those warm, sunny days in the winter. Here's another picture of that greenhouse, that naturally ventilated greenhouse. These roof panels have a large opening versus a gable vent or even a roof-type vent. So it increases ventilation rates substantially. One of the disadvantages of this greenhouse is you've got a large amount of seal area for infiltration losses. So that's a concern. But from a ventilation standpoint, they're great. We can also get naturally ventilated systems from having a peak vent and a side vent, or on if you've got a low structure, you could have just two sidewall curtains to get natural ventilation through them as well. For non-electric greenhouses, we have pneumatic controls that can be used, both on vents. Here's one that can be used on a vent up on the top, and then a couple that can open a roof vent or a gable vent, whatever. And these can be counterweighted if needed. If you've got the vent door is too heavy, they can be counterweighted. Typically, I've seen them used on cold frames and stuff, but there's no reason why they can't be used on a small greenhouse as well. Sidewall curtains. I talked to them briefly before. One of the things with sidewall curtains, they make great summertime ventilation, but they leak like a sieve in the wintertime. One is that sometimes there's single glazing, which increases our conduction heat loss, and if we don't seal them, they can have higher infiltration rates. So one of the recommendations I have is to make these things, put a wiggle wire type thing around the edge so that you can seal them up in the wintertime with something that you can quickly undo when the weather starts getting warmer in the spring to reduce the infiltration rates. Supplemental lighting, Eric Runkle is going to cover more on this. The one thing I will say is we can use lighting to get plants to market faster. If we know the daily light integral, we can measure that. So if we don't get enough sun, we add supplemental light, we can get that plant to market in a timely manner. This kind of lighting is used actually in the hydroponic business. If you're doing hydroponic greens, you want to get that crop to market. We're getting feedback. We want to get that crop to market in 39 days, and in order to do that, I've got to have an ample amount of sunlight to do that. One of the two types of lights we use in that case is high pressure sodium and metal haloid. One's on the high pressure sodium is going to give us more of a red light, where the metal halide is going to give us more of a blue light. So depending on what the stage, and Eric's going to talk more about that, but we might use high pressure sodium all through the greenhouse or a mix, a 50-50 mix. I got a couple of slides in here about solar greenhouses. I get calls and somebody says, I want a solar greenhouse. Well, greenhouses are solar. What they really want is to look at, can I do it without heating? And you can. We can use water, rock, stone, brick, whatever. We can have, thermal walls or underbench, rock under bench, or a foundation underneath the greenhouse that has, you can pipe the air down through to store heat. Cornell did a study back in the 70s, and they found with underbench rock, they could offset the heating about 25%. The biggest thing that people need to realize is you have to let the temperature vary. In order to get the heat out of, if you've got something that's 70, in order to get the heat out of that, you've got to drop the temperature. So you may have to go down to 55 or 50 to get a reasonable amount of heat out of that to maintain the greenhouse. So you've got to be able to allow the temperature to swing in the greenhouse, for one. The other issue is if I do any supplemental heating, I have to heat all that thermal mass up. So that's going to add to my heating costs to a point. So that's an issue. So there's two references I put here that I think are reasonable references that kind of cover that you might find handy. But here's just how they work. Basically, here's a brace-type greenhouse with some thermal in it. We've got a curtain here. We've got to insulate the front wall to reduce heat loss as much as possible. And we've got insulated walls here, both the north roof and the north wall, and then the east and west vary depending on the type of greenhouse. So the object is, in the summertime, the heat coming in isn't going to hit that barrels to add to the thermal mass. During the winter, the sun's low in the sky and will hit that. I'm running out of time here, so I'm going to kind of speed up. I only got a few more slides. We're almost done. So here's an example of one in western Pennsylvania. They actually use sun and wood heat to heat this, but they all will have this south-facing glazing on it. And you can see they don't have much for windows on the ends here. Just some service doors and maybe some for access. But they also be doing cold climates. Here's one in Colorado. Now, I would say their density of plants in here isn't very big, but this one actually appears to have a second story up here where they could possibly grow. And they will have, all of these will have some kind of a thermal mass in them to provide heat during the night. Here's a site if somebody's interested in trying to look at a greenhouse and how much energy you can save and how to do it. This is a site that a team that I head up has been working on, and one of them is greenhouses. So you can go in there and put the requirements of your greenhouse. So they ask you for what you want for the walls, ceiling, etc., and it will calculate out the estimated heat loss, and then it will make some recommendations on the different types of things you can do to reduce the heat loss. And depending on which ones you can select, it'll do the combined energy savings from those. So here are some references that I've found handy. This is a website that I have that kind of covers most of the stuff I've got here today. The one in red is a lot of this information came out of this publication. It's getting a little aged, but it's pretty good. A companion to that is this greenhouse engineering, and don't be scared about the word engineering. It basically is greenhouse systems, so it covers heating systems, ventilation, etc. Eric Runkle will probably allude to this lighting up for profits. It's a great collection of articles on using light to grow plants faster, better, cheaper. And then the Greenhouse Manufacturers Association has references for many things as well. So with that kind of ends today. If anybody has any questions. Otherwise, we will. We got a few minutes for questions if people have questions.
Yeah, Scott, this is Kevin. So you didn't really specifically the Focus on Energy program, but could you just briefly talk about that?
I will on Tuesday.
Oh, Tuesday. Okay.
Tuesday, we're going to do thermal curtains, and then I'm going to cover how you pay for some of this stuff.
Oh, okay. Okay, sorry.
So I'm going to talk about the REAP program as well. Okay?
Thank you.
Thank you. So we'll hopefully, if some of you that haven't signed up for next Tuesday will sign up, and we can cover thermal curtains in detail at that point. The other thing is I will email you out to the presentation today so you can have the presentation to use.
Do we get the recording of it too?
Yep, I'll send the link to that out as well.
Super. Thank you.
And the presentation and some other reference material will eventually end up on a website, so you'll have access to it.
Great.
All righty?
Would this be on our YouTube channel eventually, or where's this going to end up?
It's on the Wisconsin Extension site. They handle it, so the recording will be on there, and I'll send you a link to it and how to get to it.
Okay. Okay. So we could then forward that on to growers and let them view it.
Yep, that's possible.
Okay.
All righty. Any other questions?
Just a suggestion, when making those PDF handouts,
yep.
If you landscape it and go 4 per slide, I think the slides get a little bit bigger.
Oh, I thought I did that. Okay, yeah, I can do that. I'll do that for next time.
All right, thanks.
All right.
Bye. Thanks, Scott.
Okay, bye.